Module 14, the respiratory system. Gas exchange during external and internal respiration. The second stage of respiration is called transport. In this stage, the blood carries the oxygen to the tissues. How does the oxygen know to move out of the alveoli and into the blood, and then out of the blood and into the tissues? And how does the carbon dioxide know how to do the opposite? Well, it's due to diffusion. Remember, diffusion involves substances moving from areas of higher concentration to areas of lower concentration. And that's why the oxygen and carbon dioxide move the directions they do. If you were to remove the moisture out of air, it contains about 21% oxygen. The rest of air is made up of about 78% nitrogen and trace amounts of other gases, including carbon dioxide. Most of the air we breathe does have moisture in it, so those percentages change a bit. If there is 6% water vapor, then there's about 74% nitrogen, 20% oxygen, and the rest is other gases. Carbon dioxide would be about 0.04%. Now that's true for air that is at atmospheric pressure or at 760 millimeters of mercury. For gases, we talk about partial pressure instead of concentration, but you can think of their amounts as you would concentration. Let's first discuss partial pressure before we go any further. Dalton's law says that the pressure exerted by a mixture of gases is equivalent to the sum of the partial pressures of each of those gases. Basically, it states that if you add up all the partial pressures of the gases in the mixture, you'll come up with the total pressure they all exert. Each gas in a mix exerts its own specific pressure, so if you add all of them up, you get the total pressure. Let's look at the partial pressure of the gases in humidified air, or air with moisture in it. The partial pressure of nitrogen is found by taking the percentage of nitrogen in the air, which is 0.74, and multiplying it by the total pressure that atmospheric air exerts, which in this case is 760 millimeters of mercury. That results in 562 millimeters of mercury. And that partial pressure is a good way to measure how much nitrogen is in the air. Doing this with oxygen, we get 152 millimeters of mercury for its partial pressure, and 0.3 millimeters of mercury for carbon dioxide. This information lets you know how much of each gas is in the air. If a gas has a higher partial pressure, there is more of that gas in the air to cause that pressure. Make sense? So when we inhale humidified air, we take in nitrogen at a partial pressure of 562 millimeters of mercury, oxygen at a partial pressure of 152 millimeters of mercury, and carbon dioxide at a partial pressure of 0.3 millimeters of mercury. Thus, we know there's not a lot of carbon dioxide in air, but there's almost 4 times as much nitrogen than oxygen in it. Now, when we inhale, remember there's a functional residual capacity of air still in the lungs. You can think of it as old air that's been in the lungs for a while. Well, as the new air comes in, it mixes with the old air, changing the partial pressures a bit. That's because the old air is different from the new air, having lost some of its oxygen to the blood and having taken in carbon dioxide. When these two mix then, the partial pressure of oxygen will be less than the air outside the body, and the partial pressure of carbon dioxide will be greater. In fact, in the alveoli, the partial pressure of oxygen is about 104 millimeters of mercury, and the partial pressure of carbon dioxide is about 40 millimeters of mercury. Can you see the difference from before? Now, nitrogen amounts will not change because that gas doesn't interact with the body. Let's talk about the partial pressure of oxygen and carbon dioxide in the pulmonary capillaries that surround the alveoli. When you see a capital P, it's referring to partial pressure of the gases. Starting here, the deoxygenated blood comes into the heart so it can be pumped to the lungs. It already has given up its oxygen to the cells of the body, so it doesn't have lots of oxygen in it. Therefore, the partial pressure of oxygen at this point is about 40 millimeters of mercury, which is low. But that blood had picked up carbon dioxide from the tissues, so we should expect the amount of carbon dioxide to be higher, and it is. The pressure of carbon dioxide is about 45 millimeters of mercury. When it gets to the lungs, it's exposed to the air in the alveoli. The partial pressure of oxygen inside the alveoli is higher than the partial pressure of oxygen in the blood, so oxygen wants to diffuse out of the alveoli and into the blood. Now look at the comparative partial pressures of carbon dioxide here. The partial pressure of carbon dioxide in the alveoli is lower than what's in the blood, so carbon dioxide will diffuse from the area of higher pressure to the area of lower pressure, or from the blood to the alveoli. So there's no real directing of where the gases go. It's simply due to the differences in partial pressures, or concentrations, if you will, of the gases. They go in the direction that diffusion requires. And the gases will continue to diffuse until the partial pressure is the same on both sides of the membranes. That means that oxygen will diffuse out of the alveoli and into the blood until those pressures even out. And it's a pretty quick process due to the design of the membranes. Now, by the time the blood leaves the lungs on its way back to the heart, oxygen has a partial pressure of about 104 millimeters of mercury, which is the same amount as what is in the alveoli. And the carbon dioxide in the blood has reduced to 40 millimeters of mercury because that gas moved out of the blood into the alveoli. This oxygenated red blood moves into the heart via the pulmonary veins, as you learned when you studied the cardiovascular system. But what I didn't discuss when we talked about that system is that a little bit of deoxygenated blood mixes with the oxygenated blood as it moves back to the heart. That's because the tissues of the bronchi and bronchioles have to get oxygen and nutrients and get rid of waste and carbon dioxide, just like all the other cells of the body. So veins will take that deoxygenated blood away from those respiratory cells, dumping into the oxygenated blood that's leaving the lungs. This addition of deoxygenated blood reduces the partial pressure of oxygen to about 95 millimeters of mercury. However, it doesn't really raise the partial pressure of carbon dioxide because carbon dioxide is more soluble in plasma, so it will be carried in the blood plasma in a chemically different form. So it still has a partial pressure of about 40 millimeters of mercury when it leaves the lungs. Once that oxygenated blood makes it to the left heart, it is vigorously pumped out through the aorta so it can move to all the body's tissues. So it leaves the heart with the same partial pressures of oxygen and carbon dioxide gases as it had when it left the lungs. Now it travels to the capillaries of the body, and think about what happens there. The cells in the body tissues need more oxygen because they are continually using what oxygen they have for metabolic processes, and they've been building up carbon dioxide gas as a result. So the partial pressure of oxygen in the cells is low, about 40 millimeters of mercury, and the carbon dioxide partial pressure is high, about 45 millimeters of mercury. Therefore, oxygen will diffuse from the area of higher partial pressure in the capillaries to the area of lower partial pressure in the cells. And the carbon dioxide will diffuse in the opposite direction because its pressure is higher in the cells. Now the blood has a higher partial pressure of carbon dioxide, about 45 millimeters of mercury, and a lower partial pressure of oxygen in the blood, about 40 millimeters of mercury. And this brings us back to the beginning of the diagram. All of this discussion of blood flow and gas diffusion in the body happens pretty quickly, about 1 minute when the body is at rest. That's pretty fast. But when you exercise, the complete circuit of blood flow can happen in about 15 seconds. After this discussion, I hope you have a new appreciation for the constant need of oxygen supply to the cells of your body and the amazing design we have to meet that need.